In this video, we present our CVPR 2025 paper, CrossOver, 3D Scene Cross-Modal Alignment. CrossOver is a cross-modal alignment method for 3D scenes that learns a unified, modality-agnostic embedding space, enabling a range of tasks. For example, given the 3D CAD model of a query scene and a database of reconstructed point clouds, CrossOver can retrieve the closest matching point cloud. Please note that the virtual scene has no exact point cloud replica in the database. Using the instance encoders, it can match objects in the CAD model to objects in the point cloud, which can be aligned in the latter using a brute force method. This capability has direct applications in merging physical and digital worlds for virtual and augmented reality. Current multimodal approaches such as ULIP2 and point bind often assume perfect modality alignment and complete data, relying on synthetic datasets like ShapeNet. This is unrealistic for real-world scenarios where data is often incomplete or misaligned, such as in construction sites or robot navigation. These methods capture object-level data well, but struggle to distinguish similar instances in complex scenes, focusing mainly on isolated objects. In scene understanding, methods like scene graph lock rely heavily on detailed semantic annotations for cross-modal visual localization. Instead, CrossOver fosters organic cross-modal relationships, enabling unified understanding across diverse data types. Given a scene and its object instances represented across different modalities, namely image, point cloud, digital mesh, and referral, the goal is to align all modalities within a shared embedding space. The instance-level multimodal interaction module learns a multimodal embedding space for independent object instances. It captures modality interactions at the instance level within the context of a scene, using spatial pairwise relationships between the object instances. Despite not being explicitly trained on all possible pairwise modality combinations, but rather only on pairs where the image modality is always present, our method learns emergent modality behavior. For example, it recognizes that object I in the mesh modality corresponds to object I in the point cloud modality, without these modality pairs being present in training. This is further enhanced by the scene-level multimodal interaction module, which jointly processes all instances to represent the scene with a single feature vector fs. The instance and the scene modules provide a unified, modality-agnostic embedding space. However, it requires semantic instance information that is consistent across modalities during inference, which is challenging to obtain in practice. Now, we pose the question, how to remove dependency from semantic information? We directly process raw scene data, like scene point cloud, RGB images sampled using a grid sampling algorithm, rasterized floor plan, or text describing context within a scene, hence not needing additional information such as explicit 3D scene graphs or semantic labels during inference. The unified dimensionality encoders eliminate dependency on precise semantic instance information by learning to process each scene modality independently while interacting with the feature vector fs, thus progressively building a modality-agnostic embedding space. Once we have trained a three-stage pipeline for semantic-free cross-modal embeddings, how do we perform inference? During inference, given point cloud as the query modality, we extract a feature vector f3d in the shared embedding space. To find the most similar 2D floor plan from a database, we locate the closest feature f2d and retrieve the corresponding scene. Let's look at experimental results. Extending image feature matching evaluation, we evaluate cross-modal instance matching using recall, measuring correct matches across modalities within a scene, even with identical objects. While prior work trains on all pairwise modalities, we selectively train only in reference to the image modality I. Yet, we still achieve robust performance across all modalities, even without direct interactions during training. Second, we evaluate on cross-modal scene retrieval. Scene matching recall results show that our unified dimensionality encoders, which do not rely on semantics, consistently outperform prior methods in all pairwise modalities and surpass our baseline in most cases. The lower performance of pre-trained methods may stem from training biases that limit their robustness with real-world data, such as incomplete point clouds and blurry images. Let's look at some cross-modal scene retrieval results obtained using CrossOver on ScanNet. Given a scene in query floorplan modality, we aim to retrieve the same scene in target point cloud modality. While PointBind and the instance baseline do not retrieve the correct scene within the top 4 matches, CrossOver identifies it as the top 1 match. Temporal scenes appear close together in CrossOver's embedding space. Retrieved scenes also feature similar object layouts to the query scene. Now we showcase a failure case for CrossOver. While the baselines also fail to retrieve the same scene, CrossOver retrieves a temporal scan as k=2 match. That's it. You can find code, demo, more results, and pre-trained checkpoints on our project page. Thank you for listening.